watched a lot on in YouTube because when I forgot the timing, YouTube was already like showing it.
Okay, I think we're live.
Perfect. So shall we start? Then people will. Okay, so welcome everybody to this new session of the One World Probability Seminar. This week we are really lucky to have with us Scott Sheffield and Minjay Park. I think so. Scott's starting, and it is a great pleasure to present Scott. I think he needs no presentation, but I would like to say he has been a great inspiration for many of us in the probability world with his creative ideas that have opened new path in different directions, especially in conformal invariant geometry. And this week, he will talk to us about the Lattice Yang-Mills theory. And I think the exact title is Wilson expectation as sum over surfaces in 2 dimensions. So I give it to you, Scott.
Yes, thank you. So let me do a screen share here. Yeah, it's really great to be talking to everybody. One of the daunting things about these Zoom talks is you're never entirely sure who's going to show up. So I always wonder, there may be many people in the audience who are far more expert than I am on the Yang-Mills side, especially. I've been thinking about Yang-Mills on and off for a few years, but I still consider myself a newcomer to the subject in a lot of ways. And there may also be a lot of people who don't really know anything at all about this subject. And I'm hoping today to give sort of a kind of a gentle introduction and kind of a description of kind of what our recent contribution is, as in this paper I'm writing with Minjay and Josh Pfeffer and Puyu. And so, first, before we get started on random surfaces in Yang-Mills, I want to advertise a couple of papers on these subjects, the first by me and the others by other people. So first, I want to say that I've got this paper I just put on the archive called "What is a Random Surface?" And this is written as for the ICM proceedings. So I'll be giving a talk at the ICM, which was going to be in St. Petersburg and now is going to be online. And it's kind of an introduction to the whole notion of what is a random surface. And so, it talks about, if you're given 2 unequilateral triangles, and you look at all the ways to glue them together to make a sphere and choose one at random, there's going to be some sort of n goes to infinity limit that you could think of as sort of a canonical sphere homeomorphic random surface. And so the paper goes through and has sort of a dialogue. It's kind of informal. I talk about, what do we like if an instructor is introducing a student to Brownian motion? It's fairly simple. But then if an instructor is describing what random surfaces are, then there are sort of like 4 different ways of describing the limit. You can call it a piano sphere, a Liouville quantum gravity sphere, a conformal field theory, a Brownian sphere, and all these different stories have deep connections to one another, but they all have kind of very different surveys describing them, very different backgrounds, very different intellectual histories. So the Brownian sphere sort of grew out of the planar map stories, which came from Tutt and this 4-color problem, and it has this whole long history going out of graph theory, dating back to the 1800s, and Liouville quantum gravity, or piano-speculator starts with Moulin in the 1850s, Liouville quantum gravity. You can date back to Liouville and Gauss if you like, but it's, all of these things have kind of been gradually developed over the years as a way of kind of understanding random surfaces. And I think that at this point we have a kind of a much deeper understanding of what random surfaces are, as well as what a random surface embedded in a higher dimensional space is, like a random surface embedded in R3 or in R5 or something. What do these sort of random objects mean? And so if you just kind of look over this, it's about 60 pages, but a lot of that is references. They're like 261 references, which is still only scratching the surface, no pun intended, because it's a very large field. There's a lot of work in this area has been done. But if you look at the very last section of this article, so I have in this paper kind of one section about each of these four perspectives on that I mentioned at the beginning. So these there's the Brownian sphere, the piano sphere, the Liouville quantum gravity sphere, and the conformal field theory point of view. And so I have one section describing each of these four objects, which I hope is gentle enough that that anyone can read it. So even if you have no background in physics or in or even at all, as long as you have, you're a probabilist and mathematician, you should be able to kind of just read through this like a novel. I've tried to make it sort of conversational. And so one section on each of those four, and then a section on how they're all related together. And then there's one section at the end, just a little bit where I talk about gauge theory. And so here I didn't have much to say in this. There wasn't. I say random surfaces are related to many areas of math and physics, including random matrix theory, dimensional statistics, gauge theory, and so on. And then I note that Poyakov's famous 1981 paper starts by talking about gauge theory. So he says, in my opinion, at the present time, we have to develop an art of handling sums over random surfaces. These sums replace the old-fashioned and extremely useful sums over random paths. The replacement is necessary because today gauge invariance plays the central role in physics. Elementary excitations, gauge theories are formed by the flux lines, and the time development of these lines forms the world surfaces. All transition amplitudes are given by sums over possible surfaces with fixed boundary. And so, I mean, it's a little tricky to parse all the words in the sentence, but somehow he's saying there should be some sort of a connection between describing what we'll call gauge theories, which is a way of kind of describing a random connection, if you will, in some in Rn or on some lattice, and that these should somehow be related to random surfaces, summing over surfaces, and so also kind of say a little bit about where this belief comes from. So Poyakov wasn't, necessarily the first person to start thinking roughly on these lines, but I think his 1981 paper was really hugely influential in this area. Some people sort of mark this as the birth of the Liouville quantum gravity theory. Again, it's more complicated if you look into history. There's a lot of stuff before, a lot of stuff after. So it doesn't really start with just one paper, but this paper did kind of launch, I think, a whole theory of random surfaces, as well as this whole big question of what exactly is the relationship between random surfaces and these gauge theories. So what they call gauge string dualities. So the problem of understanding these Yang-Mills gauge theories, many of you know, is a Clay Millennium Prize problem. If you solve the problem, you get $1 million. And the problem is basically trying to describe a continuum version of these lattice gauge theories and prove sort of the most fundamental expected properties of this theory. And kind of from the beginning, there's been a question of whether these surfaces, random surfaces, would have some help in describing this. And it's been controversial from the beginning. So there's this paper I'll show you in 1995, which had a whole dialogue between the skeptic and the enthusiast. The skeptic who really thinks this approach is never going to work, it's hopeless, you should try something else. And the enthusiast who says, no, random surfaces are really the key to understanding the gauge theory problem. We should really approach gauge theory from the point of view of random surfaces. And even today, there are things called AGT conjecture, ADS-CFT. There's a huge literature on people doing things that are somewhere in the realm of trying to say something about this connection between these gauge theories and these string theories. So, to show you a couple other more papers before I start actually giving some definitions and things. Well, actually, maybe I'll maybe before I say more about some of these papers, I'll go a little bit to the definitions, and then I'll come back and show you a few of these other things. So, okay, so first, some basic definitions. So,
excuse me.
Yes, go ahead.
Oh, sorry. So I was seeing your first slide for a long time. So you just started with the second slide?
Okay, so let me stop share and make sure that you're shared properly with the. Okay, can you see this now?
Yeah.
Okay.
Yeah, sorry.
Good. All right, and you were seeing what I was doing before, right? On the.
No, I was only seeing this slide for a long time.
No, we haven't seen anything.
You haven't seen anything? Why do people not interrupt me and tell me this?
Yeah, I thought you were wanting to give us just the idea and keep in the first page.
Okay.
Sorry.
Okay, so sorry. What right. Okay. So what I was showing you was this. Yeah. So here was this. This was the paper I was describing. This is it's on the internet with what is a random surface, and I was telling you these different types of. So this is the ICM notes. So this is the picture of kind of a. If you take a. This is by Budzinski. If you take a random triangulation with uniformly among all ways of making a sphere out of a large number of triangles, you get a random surface like this. And if you want to understand what's the infinite kind of the scaling limit of this, as the number of triangles goes to infinity, there are these various approaches. One called the Brownian sphere approach, one called the piano sphere approach, one called the Liouville quantum gravity sphere approach, and one which is what we call conformal field theory, which is kind of a multi-point formalism of kind of you think of these things in terms of what they call fields, which are defined at points, and try to compute expectations of things like that. So there's these four kind of completely different ways of describing a random surface. And so this paper is just telling you what these four approaches are, and one has one section kind of detailing each of these four approaches. Okay, and so and then I was pointing out that if you go to the end of this paper, there's a very short thing about a very short introduction to gauge theory. I mean, just extremely short, but just pointing out that we have this famous quote by Polyakov, where he kind of was one of the really influential people starting the line of thinking about trying to connect these random surfaces to problems in gauge theory. And there are a few links here to papers, which I'll say a little bit more about in a minute. Okay, good. So now, Lattice Yang-Mills theory, the lattice version of this, assigns a random n by n matrix from some compact group of matrices to every edge of a d-dimensional lattice. And so you think of it as taking a hard measure, which is kind of the uniform measure on the whatever the compact group of matrices is. Maybe this is SUN or SON. And you weight it by e to the some of the real parts of the plaquette traces. So, I'll say a little bit more about that in a minute, but, for every plaquette, every square in your lattice, you can multiply all the matrices around that plaquette and look at the trace of that. And if that matrix is the identity, then that trace will be kind of the largest it can possibly be. And if the trace is not the identity, then the real part of the trace will be some kind of smaller value. And so if you weight by each of this, you're sort of favoring things where the product around every plaquette is the identity. And so the Yang-Mills problem is, roughly speaking, to try to construct and understand the basics of a continuum version of this model. And the big problems are to understand this when D is 4 and when you have an n by n matrix for some small n. So in the standard model, the gauge group is, say, UN cross SUN cross SU2 cross SU3. And so if I define a random collection of matrices this way, so again, it's one matrix for every edge, then I can ask, what's the expected trace of a product of matrices in a bigger cycle? So I can take a long loop, these are called Wilson loops, and ask, what is the expected trace of the product over all the matrices in this loop? Or if you like, I can take the product of traces over multiple different loops and ask, what's the expectation of that product of traces? And that's kind of the fundamental object in the theory. Okay, so it's very simple to define. You start with just taking an independent random matrix for every edge. And then you just take a sort of weighting that wants to say, so an independent matrix for every directed edge. So if you go the inverse direction, you'll get the inverse of the matrix. And then you just do a weighting that makes it so you want the product of the matrices around every plaquette to be close to the identity. So if I were going to go up to the board here, you just imagine you have some sort of a lattice. 2 dimension is very simple to draw. And then for every edge, every directed edge here, you have a matrix. It says M1 for this edge, M2 for this edge, M3 for this vector edge. If I reverse the direction of edge, I just take the inverse of the matrix. So the matrices correspond to the directed edges, with the inverse corresponding to the inverse direction. And so for every edge, I have a matrix. And I start out by imagining the matrices are just independent from one edge to another. And then I say, well, for every plaquette, the plaquette is a square like this. For every plaquette, I can ask, what is the product of all of the matrices corresponding to that plaquette? So if this is M1, M2, M3, M4 around this plaquette here, then I could just take the trace of M1, M2, M3, M4. And I assume you're all seeing this, and will interrupt me if you can't see. Okay, good. And so this trace, so when I take this product of the matrices, these are all a subcompact Lie group. If the matrices are all kind of close to the identity, then this product, it's just
okay. We see it, but it's tiny. We do not really see.
You can't.
It's really tiny, so somehow
you can't see. Oh,
I can't see correctly, but maybe you can.
You have to somehow pin me to make me large somehow.
Yes.
Can you pin my maybe I can do
speaker
that.
and.
So if I click pin on me, does this make me big now?
Now I see it, yeah.
Now you see it big. Okay, good. Thank you. Okay, so yeah, so basically, if these, so we refer to this set of matrices as a discrete version of a connection. So a connection is a way of doing parallel transport. What that means is that if I give you a path, I mean, in sort of space, you can imagine if you slide without slipping around a surface, then your orientation might change. Or as you go through space, your orientation might change. And so you have some sort of group of rotations. And as you move along a path, you also, that induces a path in the group. And in general, if I give you a way of taking a path in space to a path in a group, that's called a connection. Just a term for it. And so here, and in order to describe it, for every edge, I have to give you the matrix, the group element. And so as I go around this path, the parallel transport, when they call it, this connection is to say I just multiply first by the first group element, then by the next, then by the next, then by the next. And if you're in what you call a flat metric, then that means when you go around a loop and you come back, you haven't changed your orientation at all. So you know that if you're like on the surface of the Earth, you start at the equator and you slide without slipping up to the North Pole. If I start with my hand like this, I slide to the North Pole, slide back down over to the West Pole, slide back over to here. Then magically my hand has been rotated by 90 degrees. If I do it again, over, then it rotates another 90 degrees. And so, so the sliding around the surface has, around a loop has the effect of giving what they call a holonomy, which means as I go around the loop with this sliding without slipping, I come back and there's been some element to this set of rotations, you know, this happened. So going around a loop effectively gives me a group element. And this, you can imagine, it could work for general groups, not just the group of a group of transformations of the tangent space, the group of rotations. It could be for any. You can imagine I give you a path and you assign a group element to that path, and that's what we call a connection. So somehow I assign a group element randomly to every edge of the lattice, and that's what we call a connection. And now if I wait, I assign an energy, which is the sum of all of these the real parts of the traces. I take the trace around everything, take the real part of that, and that's going to give me, in some sense, a measure of how far the matrix is from the identity matrix. So if you take the identity, the trace is maximal possible. If you take, negative the identity, which is the furthest from the identity you can get, the trace is the smallest it can possibly be. In general, the closeness of the trace to 1 is some sort of a measure of how far the closest of the trace to the maximal value is a measure of how far you are from the identity. And so the minimal energy thing will be when the traces are all the maximum possible, and then this would be sort of the maximum possible energy, and you just wait by e to this energy, or even some constant times this energy, and that gives us a random, what we call a random connection. It's really just a random function from the edges to the matrices, where when I reverse the direction of an edge, I reverse I replace the matrix with its inverse. Okay, so that's the model, and the question is, understand the scaling limit of this model in dimension 3 or 4. And as far as winning the $1 million, you don't actually have to take the scaling limit of the discrete models. You just have to give a satisfactory continuum theory. And so if you had a way of constructing the continuum object that didn't involve going through the lattice, that would also get you full credit. And so that's significant because, sometimes like something like the Ising model, proving that, say, the Ising model interfaces converge to SLE3 is a problem separate from the problem of just constructing, say, SLE3, these random curves. These are sort of separate problems. So you can say the lattice gives you motivation, but if you have some other way of describing the continuum object, that would be satisfactory as far as this theoretical question of describing Yang-Mills goes. Okay, let me go back to the screen for just a minute. Okay, so now what we can do is we define these objects. So for any loop L1, I can define W of L1 to be the product of the matrix, the trace of the product of the matrices around that loop. So if L2 is a loop, WL2 is the trace of all the products around that loop. And I can define F of L1, Ln to be this product of traces. So for example, going back up to here, I could take a loop, a bigger loop, say to be this path here. I go around some larger trajectory, and I can ask, what's the product of the traces around this loop? And since I'm waiting by the energy to try to make the product around every plaquette close to the identity, and you might think that for the slightly larger loop, the product of traces would be sort of close to, close to the identity. Because it's close to the identity around every small loop. That might mean this product overall is close to the identity as well. And certainly, if you glue two things together, if this is the identity and this is the identity, then this has to be the identity as well, because you can write it as this followed by this. And so somehow, if you had what they call a flat metric, these loops would all be the identity, but in general, they won't be, and there would be some expectation for the trace of this. And somehow, in the physics theory, they're convinced that the relative question is just understanding the expected traces of these loops, of the matrix product around these loops. And if I wanted to take not just one loop, I could take like two loops and say, take the expected product of the trace around this loop and the trace around this loop. And that would also be an interesting question. And this collection of loops is sometimes called a string. So it's some finite collection of loops. And so you want to basically assign a number to every string, which is what they call the Wilson loop expectation. That's the goal of this theory. Okay. And sometimes in this math, you can derive using integration by parts. Chatterjee's survey, has a nice description of this. Something they call a master loop equation, which somehow says that this function f behaves as though it were a sum over spanning surfaces. And what do I mean by that? Well, okay, let's go back to the this picture here. Imagine that we were just taking a sum over surfaces spanning this loop. So what would a surface be? Well, maybe a surface is a collection of squares that are glued together on their boundary, kind of embedded in this space here. So you can kind of think of it as, you take a planar map made out of plaquettes, and you map that, you take a function from that planar map into this lattice that maps every plaquette to a plaquette here. Every square in the planar map gets mapped to a square here. And you could do this in any dimensional space. Imagine you have this sort of map from your surface, which is just a collection of squares glued together along their boundaries. You have a map from this into your space. And you can imagine if you had some sort of a sum over all the surfaces that you can make, infinitely many possible surfaces you can make that have, say, this string as their boundary. These two things as the boundary. What's the sum over all surfaces that have this pair of loops as the boundary? And well, if you took a sum over all those surfaces, then you would expect to have some nice property that you could ask, well, starting at this edge, if I'm summing over all surfaces, I can ask, what is the surface connected to this edge here? what's the square of this surface connected to this edge? And it might be that if I observe the square connected to this edge, it's a square down here. Or it might be the square connected to this edge, it's a square that goes out of this thing here way. Or it might be that the square is one that comes up here. It's just this square here. And there's sort of finitely many possible squares that could be the square in the surface that has this as its boundary. And I can kind of sum over those possibilities. So if it's this one, and I tell you that this square is part of the surface, then given that, I now have to sum over all the surfaces with this as its boundary, this new piece. If I told you the surface was out of the screen, then you'd have to sum over all the surfaces with this as its boundary. So somehow what you'd have to say is that the original sum is a sum over, the original Wilson loop expectation is some sort of a weighted average of the Wilson loop expectations corresponding to perturbations of this by replacing this edge and replacing it by 3 other edges or something like that. And so this is kind of what they call it the local equation. And there are discrete versions of this that they've been able to prove where you say that this surface sum is some weighted average of neighboring. The trouble is that when you do these weighted averages, it typically tends to be that it's not an average in the usual sense. It's a linear sum of the neighboring objects, but the weights are not all positive. They don't all add up to 1 necessarily. And so, you have some sort of a sum over spanning surfaces, but the weights are complicated. And in general, these sums, sometimes when you actually try to make sense of it, you get differences of infinities. And it doesn't necessarily always work out nicely. Okay, let me go back to the screen. Okay. And so the surface sums, when you do it, it turns out it sometimes become weighted by genus, and they're higher finite genus versions of things that appear. I'm going to say more about this just in a minute. So, so there are variants. So you could take for any lattice D, you can try to make sense of Yang-Mills. The D in 125, this is the range for which we have some sort of a random surface model in the continuum, although again, the connection to discrete is hard to know how much that will help. You can change the measure on groups. You can take the Gaussian, you could use a Gaussian measure, for example, instead of a compact group measure. You can take the matrix group to infinity, n to infinity instead of a finite n. You can change the weights on your plaquettes to polynomial instead of exponential. You can change the temperature. There are all sorts of things you can do. Okay, so let me kind of skip ahead to here's some notation that you'll find, for example, in Chatterjee's paper. You say a path will be just a sequence of edges, E1 through En. The cycle is kind of an equivalence class of closed paths where they're equivalent if you just change the starting point and start from a different point. A string is a finite collection of paths. And so in this paper, and I'll show you here on the, if we go to, let me just make sure that you're on this screen. So this paper I'm going to mention is this, Chatterjee has a survey paper called Yang-Mills for Probabilist, which surveys several papers that he's worked on recently, on kind of giving a nice description, especially of the lattice version of this theory. And okay, and so what he finds is that there are certain operations you can do that correspond to what I would think of as these little local changes to the string, where I'm saying you sort of observe the plaquette next to the string, and maybe you find that it's connected to another string or another string with kind of twisting around in some way, or it's they're the things that can happen as you sort of start exploring your surface. And he finds this sort of this relationship where the Wilson loop explanation, the Wilson loop for one string can be written as a weighted average of the Wilson loop expectations for neighboring strings. Okay, and just to make it clear, it's always the case in this theory that if you have a trajectory in the space of strings, so if I start with this string and I make a little local change to it, and then another local change, another local change, and I keep making those local changes until at some point I get to like the 0 string, that trajectory in the space of strings is thought of as tracing out a surface. We sometimes call this the world sheet. It's a trajectory in the space of strings. And so you can sometimes imagine if you were summing over all possible string trajectories, then you'd somehow be sort of summing over all possible surfaces together with sort of an exploration of the surface. Okay, and so your plaquette is a product of edges that forms a square. You can define a matrix QE for every edge, QP for every path. You can find WL to be the real part of the trace of Q of L, and because the trace is invariant under cyclic rerouting, it's a conjugacy invariant, then this is something that is defined for the loop without knowing. You don't have to specify where you start on each loop in order to define this these WLs in order to find this expectation, the expected product of these things. Okay, and so really the whole theory is you want kind of continuum version of understanding this object. And then the measure you get is Q. You think of Q as the set of QEs where E ranges over all possible directed edges. Your measure is basically you start by this, which is like your Haar measure on this bed of the product of the Haar measure on all the matrices. You weight by this e to the n beta times this product of these traces. So the trace corresponding for every path, as I mentioned earlier, and then you kind of normalize to make it a probability measure. And this is what you want to understand. Now, this question, how far is the unitary matrix from the identity? If you look at a matrix like UN, the distance from Z to 1 can be written as 1 minus Z squared. But you can also write that as 1 minus Z times 1 minus Z bar. If you think about it, that's equivalent to 1 minus 2 times the real part of Z. That's 1, which is just 2 minus the real part of Z. So somehow, if I want to understand the square distance, that's equivalent to understanding just the square distance in Z, this complex number from 1. That's equivalent to saying what's the distance between the real part of Z and 1. So this is sort of a square distance, or real part of, and this is a distance, but because you're restricting Z to the unit circle, they magically turn out to be the same. So when we say we're taking the trace, it really is literally a measure of the distance of the matrix to the identity, because of the way we're restricting to these things with whose eigenvalues are all, these are all compact groups, so the eigenvalues are all going to be roots of unity. They're all going to be things with complex modulus 1. And so I just want to say in general, this quantity n minus the real part of the trace is a measure of the distance from the identity in the same way that trace of identity minus A1 minus a trace. This would also be seen as a measure of the distance from the identity. This is just sort of like the L2 norm of I minus A, which is just the usual way of thinking of the distance from A to the identity. This is kind of an equivalent way of doing it. It just involves the trace. And so this is why the trace comes up everywhere. Okay. All right. So the energy, it's really just a sum over all plaquette loops, or somehow the distance from the identity, if you like. Okay. All right. And so gauge fixing, this is a very important concept, is that you can reduce your number of degrees of freedom. And somehow fiddling with gauge choice, you can, let me just say what this means on the board a little bit. I'm going to stop share briefly and say, if I tell you that we're doing this model on this collection of, I'm getting a random matrix here for every one of these edges. You can easily see that the energy doesn't change if I multiply all the matrices in this thing by a fixed matrix. So there's some symmetry. There's also a symmetry more than that, which is that suppose I take the directed edges going, the matrices going into this vertex. So I have some directed edges going into this vertex, and say E1, E2, E3, E4 are the directed edges going into this. And so I have these matrices QE1, QE2, QE3, and QE4, which will describe the matrices for each of these inwardly directed edges. And then you might ask, what happens if I multiply each of these matrices on the right by some other matrix? Maybe I multiply this by some matrix M, this by an M, this by an M, this by an M. You see what happens then is that when I look at the product of matrices around the loop, I get, well, this matrix times M. But then when I go this way, I get the inverse of this matrix times M. This matrix here times M. And that, I take the inverse of AM, that's going to be M inverse A inverse. And so when I go around here, I take matrix times M, and then M inverse times this inverse. So the M and M inverse just cancel out. And I end up getting the original thing back. So somehow, this is what they call a gauge transformation, which is you take each incoming matrix here and you just multiply it on the right by a fixed matrix. And the whole theory is invariant under doing this. And so the idea is that by applying these gauge transformations, I can sort of reduce the problem to something simpler. So what you could say is, like suppose I tell you that no matter what, I'm going to choose this matrix M to make it so that this edge here is the identity. Okay, so whatever you give me, I can always, whatever system of matrices you give me, I can always choose an edge to make this, choose M to make this the identity. And the point is that when I do that restriction, that doesn't change the kind of condition, the law of any of the other loops expectations, because the overall measure is just given by taking this restricted measure and then tensoring it with just kind of independently choosing what the matrix on this edge would be.
Scott, there's one question on the chat. They're asking
yes.
whether there is a role of free probability in this version of Yang-Mills.
Yes, free probability definitely comes into play in this version of Yang-Mills. And that's especially relevant when you take n go big, the dimension of the group going to infinity. So free probability is all about what happens to random matrix theory when the dimension of the matrix goes to infinity. And it definitely comes up here. I'm not going to say more about it in this talk, but there are definitely a lot of connections there, yes.
Thank you.
And so the thing is, so you can sort of reduce to the story where this is fixed to the identity. And in fact, if you think about it, if I take any spanning tree, I can always apply these gauge transformations at vertices along the tree, start here and then start at one vertex and then apply gauge transformation to each of the subsequent vertices, I can do it to reduce to the case that, that all of these edges are the identity. So I give you a tree like this, you can start at this vertex and then apply gauge transformation at this vertex to make this the identity, one over here to make this the identity, one here to make this the identity, one here to make this the identity. And so then they're all the identities. So the problem, if you like, an equivalent problem, the original Yang-Mills problem, is to say, fix a spanning tree. This works in any dimension. Fix a spanning tree of your graph and pin all the edges of that to be the identity. And then do Yang-Mills on everything else. So you just have to pick a random matrix for all of the other edges. And again, you're weighting by the product of these plaquette traces, or E to the sum of all these plaquette traces. But now these traces, they're a little bit simpler because in this case, 3 of these edges are fixed to the identity, and so it's only one edge that I have to worry about in this case, in this particular spot here. And in general, there may be 2 edges, but there are always going to be fewer edges. If I took a whole grid like this, for example, one natural thing to do might say use gauge fixing to make it so I have the identity on the bottom row, and I have the identity on all of these vertical lines. And then I just have a random matrix for each one of these edges here. Okay, and then this looks a lot simpler because it actually ends up being extremely simple in this case, because in this case, there will be some trace corresponding to this loop here, some trace corresponding to this loop here, and some trace corresponding to this loop here. But if you think about it, if I call these matrices here M1, M2, and M3, then the trace corresponding to this loop will be, I have some trace of M1. Here I have, this will be like some trace of M1, M2 inverse. And here the relevant thing is some trace of M2, M3 inverse. But if you think about the law defined by this weight, it's sort of Markovian in the sense that this measure is somehow telling you the difference between M1 and M2. It's the trace of M1 times M2 inverse, which is really just kind of, you're weighting by the difference between M1 and M2. And here is the difference between M2 and M3. And here is this difference between the identity of M1. So it's really like you have your 3 matrices. In this, you have the identity, you have M1, you have M2, you have M3, and you're really weighting by kind of either the sum of these distances. And if you think about it, that means that these matrices are just going to be kind of like a random walk. This will be, you'll have some random thing for M1, given that M2 is some random thing weighted to be close to M1, given that M3 is something randomly weighted to be close to M2. And if you're at low temperature, M1 will be very close to the identity, M2 will be very close to M1, M3 will be very close to M2. But you really are literally just taking a random walk and doing it for each of these guys. And if you
but
want
I have to bother you, so you have like 5 minutes left.
Okay, right. Let's see. Yeah, so what is it? This ends up working out very simply in 2 dimensions. So you can take any spanning tree you like, and So for example, let me draw another. I could take my spanning tree to be something like this. Well, maybe with one opening at the bottom, and where you really get for the matrices, you just have some kind of Markovian path on a set of matrices. So in some sense, this is very simple. You're just taking a random walk on the Lie group, essentially, as you kind of snake through this tree. And well, I see. I want to make this a snake, so you just take some random walk through this thing, and then your trace is just going to be like, what's the value at the end? So if I wanted to do the Wilson loop expectation for a kind of a large simple loop like this, it essentially corresponds to the Wilson loop expectation. Essentially corresponds to just doing a Brownian motion on a Lie group up to some time from the scaling rule, just doing a Brownian motion on the Lie group up to time, looking at the expected trace of that. Now it turns out if you take more complicated loops, like a loop that looks like this, then the theory is in some sense still simple, but you're going to get the expected trace of some sort of a word whose entries are objects obtained by doing a Brownian motion on a Lie group up to some time. And so you get the expected trace of some word in these guys. And so it's still in some sense simple. It's far simpler than trying to understand the continuum theory. But these expected traces of words in products of matrices are kind of interesting. There's a lot of beautiful, interesting combinatorics in understanding these objects. And it turns out that there's a very precise sense in which these expected traces can be described as sums over surfaces that have these loops as their boundary. And that's kind of what Minjay will say a little bit more about in his version, is that we worked on trying to say that, at least in 2 dimensions, there is some sort of a sum over surfaces with this loop as its boundary that describes this Wilson loop expectation. Now let me go back to the, I promise to show you very quickly a little bit more of these other papers. So this is a paper, proving this Marcinko-Migdal equation, which is really a way of understanding Yang-Mills theory in the plane and how these values change when you make little perturbations to these systems of loops. And so we have kind of an alternate proof of that. I mean, this is 3 proofs. There were proofs before this, but we give one more proof with our point of view. This is Terry Levy's paper. He has this wonderful asterisk paper where he actually goes through and he finds the expected traces corresponding to different types of loops. So if it's a simple loop, the expected trace is e to the minus s over 2. But if it's a figure 8, well, it's also e to the minus a half times the area enclosed. But then when you get these other more complicated loops, you get these more complicated formulas. And it turns out you can understand these formulas as counting somehow the number of surfaces spanning these loops. But these surfaces have to be thought of as, in some sense, kind of like branch covers, because you have, if a loop goes around twice, there may be, if you kind of map a disk into this, there may be a point where there's a ramification where, like if you take the map from z to z squared, it's like a double cover, and then 0 is a special point where, and choosing where to put those sort of special points kind of contributes these polynomial terms. And so kind of our work is kind of trying to understand these formulas that Terry Levy has in kind of a more geometric way. And we're not really the first people to think about trying to do this sort of story. So this here is this 1995 paper. This is by, I'll tell you the name at the beginning, Cords, Moore, and Ramgulam. And they have this wonderful dialogue here between what they call the string theory enthusiasts and the string theory skeptics. The people who really believe these random surfaces will be useful, and the people who think this program is never going to work. Enthusiasm says, yes, string amplitude satisfies duality property. Well, yes, but it's going to be hard to do anything other than phenomenological. Some talks about these planar T-hoof diagrams, surfaces, and others says, yes, I agree with that, but I think it's only going to work for lower orders of perturbation. Some says, well, these Wilson loops are easy to understand because we have these Migdal-Kinko equations I was describing, which can be thought of as like a Laplacian on the space of loops. And the skeptic says, yeah, but Laplacians on space of loops are hard to normalize. It's hard to understand the limits. And the enthusiast says, well, yeah, but there's this strong coupling theory that corresponds to what Chatterjee does. And the skeptic says, yes, but it's the surfaces are going to intersect in complicated ways. The sum will be useless because it's so complicated. And he says no, and there's kind of a back and forth. And the interesting thing is that even the things that the skeptic and enthusiast both take for granted, like, oh yeah, you can do this. Well, you can't do this. Oh yeah, but you can do this. The things that say, oh yeah, but you can do this, are still things that take a lot of work for us mathematicians to understand. Because they're, when they say, yeah, you can do this, even the, yeah, you can do this things are not necessarily defined in a level of mathematical rigor that would satisfy us necessarily on the mathematical side. And so a lot of what we've been doing is just trying to do the things that they're sort of taking for granted here, that you can obviously do. At the end of the day, he says, yes, but in 2 dimensions, everything is wonderful. It's, SHAP brings into focus, there's stringy signatures, the gross program has some success. And what we're trying to do is understanding this in a different way. And so when they understand this, they mostly use representation theory on the compact group. So if you take a Brownian motion on a compact Lie group, you can understand it in terms of the Laplacian on the group, and the Laplacian you can kind of write it in terms of, you can kind of diagonalize the Laplacian using the characters of the representations on the Lie group. And so they have a way of describing this using representation theory, and we kind of have an approach that doesn't use any representation theory and is sort of more probabilistic. And that's what Minjay is going to describe for you in his talk. So far I've just done some big picture storytelling, explaining what the overall problem is, but maybe should I stop and ask if there are any questions before we move on to Minjay?
Well, first, thank you, Scott, for your talk. I had some questions on this. The basic of story of the Yang-Mills. So, for example, good accumulation points of the theory suffice as saying this is a continuum theory.
What a what point? Sorry, an accumulation.
Accumulation points. Yes.
Yeah, that's a good question. So if you could show that these things have a subsequential limit, but not necessarily a limit, are you going to get the $1 million for doing that?
Yes, that's a question.
If you could show that these subsequential limits exist, and any subsequential limit has the properties. So, for the $1 million, you also have to prove the limit has certain properties that they expect.
Should I show that all of them, for example, satisfied, or just one of them satisfies?
Just one of them satisfies it? I don't know.
Would I get my $1 million?
Have your lawyers negotiate with the Clay Institute. I think, obviously they want to have a clear description of the theory. So if you just said, there are many possible subsequential limits, and at least one of them is well behaved, they might not think that was good enough. But I don't know. You can ask 2 questions. What gets you the $1 million, and what satisfies me personally? if you want to make me personally happy, I'm happy with any progress at all you can get in this area. It's such a complicated, difficult subject that I will invite you to MIT and give you whatever accolades are in my power to give for much more modest achievements. So I think anything you can do is great. And so understanding subsequential limit is wonderful. As far as the $1 million, I mean, that's a question that you have to take up with the Clay family, I guess.
And well, I think that this we will see with Minjae stock, but is like abelian groups easier in your setup? Or
say it again.
Are abelian groups easier in your setup? Or?
Yeah. I mean, abelian groups are yeah. I mean, it's I guess in some sense. Yeah, I mean, the abelian group is sort of everything is easy for abelian groups, I guess, because in that case, essentially instead of doing Brownian motion on one of these Lie groups, you're just doing Brownian motion on like a circle or something, which you can just lift to Brownian motion on a real line, and it's kind of it's a simpler theory, yeah.
So are there any other questions? So,
go ahead.
Yes.
Maybe I should stop the share.
So we can see you bigger.
And so maybe even stop the me.
Yes. So I
should.
So anyhow, Scott, I imagine is staying also for Minjae's talk. So maybe if people have other questions and they feel shy to ask them now, they can ask them at the end of Minjae's talk. And I would like to that we all open our mics to thank Scott for the wonderful talk. And let us take 5 minutes so we can start Minjae's talk and people can go and look for their coffee.
And Scott, do you mind if I upload the slides, combined yours and mine?
Yeah. You put anything up if you want.
Yeah, sure. I will put it on the chat so that people can review.
All right, you just have to do everything I didn't get to.
The slides I uploaded is kind of duplicated in some sense for the background, so maybe people can be more happy with more resources to look up.
So it works fine, the slides. I have them now in my computer. So if you feel comfortable, you can now start sharing the slides. So if we see if everything is going. Oh, I think you are sharing your tablet, no?
Oh, yeah.
Yes.
So I will not repeat the backgrounds and motivations. So maybe I can start from here.
Yes. So let me me present you. I hope that they don't start walking behind me. Okay. I was just looking at the time. If I promise 5 minutes, I think I did 5 minutes. I'm not perfect. So okay, let us start with the second talk of this day. I don't know if evening or afternoon for you. We have the pleasure to have with us Minjae Park, who is a student of Scott at MIT. He's in his 5th year of PhD, and he will continue the topic of Scott's talk.
Okay. So as Scott nicely explained the motivations and what we are doing, so I'll omit that part. And from now on, we will focus on the two-dimensional case. And in particular, we want to also focus on the plane case, because there, everything is very simple and clear and beautiful. So the formula we are going to use for the plane case is called driver-Sengotta formula. So this is some sort of like continuum version of that lattice gauge in two-dimensional case, but it is very well defined for any finite graphs, and it is invariant under subdivision. So we can define continuum limit using this formula. So what this formula basically is saying is that, as Scott explained, there's some like product of higher measures on the edges, and instead of having some Wilson action in the discrete case, we will weight this by some heat kernel, evaluate some holonomies. So the implication of this formula, which matters for us, is that if you consider some simple loop, which has the area, let's say absolute value of f, then the holonomy of this loop will be the Brownian motion on the Lie group G we consider. So in this way, we want to somehow reduce our problems to compute the Wilson loop expectation as like first you decompose your complicated loops as some concatenation of disjoint loops. And then we want to just compute the expected trace of product of those Brownian motions. So before giving details, to give a sense what we have done and what we have contributed in this topic, I will very simplify our result. So let's say we have some rectifiable loop in the plane. So like the loop can be very weird like this, but as long as it is rectifiable, you can define some bounded faces like F1, F2, F3, F4, and so on. And for each face, you want to define some independent copies of Brownian motions on the Lie group G. And this Brownian motion is from for the Lebesgue area of each face they correspond. Then it is known by several people that the Wilson loop expectation of this loop is given by the product, or actually the expected trace of the product of these random variables and their inverses. So we will see how these products will be made from the loop later, but for now, let's just assume that it is just a product of some random variables given this. And in the above setting, what we have shown is that we can compute the Wilson loop expectation as sum over some surfaces in the following sense. So first, let's assume we have some words. So to make the notation simple, we will just say we have some words that consist of, say, m words, which might have some inverse of its alphabets like this. And each word is corresponding to some Brownian motion that run for some corresponding Lebesgue area of the face. And its Brownian motions are independent. But if they have the same alphabet like this, or even though they have the inverse relation, they come from the same source of the randomness. So from such a words, we can recover some sort of a product of random motions. And we will just say, denote it as something like this. And we want to compute the expected trace of these products of random motions. And there is a thing we want to compute. And to do so, what we have is some set which consists of the pairs which have the same index in this word or in the product. So what I'm saying as the same index is that if they are coming from the same source of the random variable, then we pair these ones and we record, say, give their locations like this. And we record this pair in this set. And also there is another pair like this. And there's another pair here. So at this point, we don't care about whether they are in inverse relation or not. And what we are doing is we just make some cyclic order to make some polygons like this. And then we pick some Poisson point process from this sigma. And each point, say, so here there are 3 points. And we consider Poisson point process made from this sigma. And they have their own rates, which is just some corresponding area of the that we define here. So this elements has this rate. And we can pick some ordered Poisson point process from this set. And that will define some sequence of pairs. And using the sequence of pairs, we want to glue the edges of this polygon. So let's say the sample of Poisson point process is like 2, 5, 3, 6, and 2, 5. Then what we want to do is, so we somehow glue these 2 and 5, depending on some rules. That only depends on the gauge group we choose. And then, so for now, let's say our gauge group is U of n. And this gluing rule also depends on whether they are in the inverse relation or not in the original word. But for now, let's ignore that. And in the U of n case, the gluing rule is just some very naive. So you pick some points and you glue that in an orientable way. And the next one was 3, 6. So the next gluing happens along these lines. And again, the next one is happening in the 2, 5. And this gluing might be happening in the reversed order or disorder, but it depends on whether they were from the inverse relation or not. Anyway, using these relations. So what I mean by gluing these points is that you somehow consider some infinitesimal elements along that points and you glue them. And by shrinking other points to the point, then you will get some surface. So our results is saying that, so if you do this process and construct some random surface, then the Wilson loop expectation is the expected sine power of some Euler characteristic of the surface we constructed. And multiplied by some e to the total area divided by 2. And there could be some normalizing factor that comes from the Poisson measure. So to give,
sorry, Minjay,
yeah.
I have a question.
Yeah, sure.
So when you do this procedure, you are gluing against itself or with a copy? So my question is, what happens when you have two times 2, 5? I didn't get that part.
Okay, so there might be 2 types of gluing process, so that I will explain later if I have time. But it might be happening so that so let's say these are 2 copies. It might be possible that you glue these 2 edges like in this order, or it might be possible that you glue the edges in reverse order.
Yes.
But it depends on whether your original gluing come from the inverse relation or not. So in the
Yes.
first, yeah.
But
Yeah.
what happens when you have to, because you have a Poisson point processor, what happens if the same edges appears twice, that you have to glue them?
Yeah, so you will make some ordered points on the edge, and you will glue different positions along the edges. So because
okay, so you're not gluing all the edges, just one. You're adding one.
No. We add the points, but this Poisson point process will be ordered uniformly. So there is a sequence.
Okay.
So we can give some natural order along the edges, and you can define some order of points where it will be glued.
Okay. I thought that you were gluing everything.
No, yeah.
Thank you.
So to see how this works for some complicated real example like this. So here it is quite simple that this loop, so my loop is given by something like from here, like this. So this is A-shaped loop, which is like complicated enough. And in that case, you can write your loop as product of disjoint loops. Like for example, to write the right parts, you can first start with A and then trace C, where there is a backtracking which cancels these parts, and you can go to B again, something like that. And you can say the original loop is concatenation of these disjointed loops like this. And in this case, the only pairings that are possible is these A's and B's. So in this case, we construct our pairing set as this two element set. And first of all, this first part is corresponding to the e to the negative total area divided by 2. So by total area, it means there are 2 copies of A and 2 copies of B, and 1 copy of C and 1 copy of D. So we just add them and divide by 2. And the next terms seems quite complicated. But if you think of this original formulation that we have this A inverse. So for now, the only thing that matters is A and B. So let's just write A and B here. Like this. And suppose that you have like no points in the Poisson process, then that will contribute to you to just 1 in this term. And the second term might contribute from the process that glues. So there's 1 point from A inverse and A pairing. And in that case, you just glue these points. And we will make some genus 0 surface. So that will just contribute to A. And if you have 2 copies of like this first elements, then you it's because of they are in the inverse relation, but the gluing happens like this. So in that case, you will have A squared over 2 and so on. Also, if you have like only B copies, then you will also have this kind of terms. And what happens if you have at least one of A and B's? And in that case, there's some crossings happening. And if you glue this surface like this using this gluing rule, then you will have some surface that has genus 1. And it doesn't matter how many copies you have here. So they will contribute to these terms. But in that case, because you have genus 1, it will have weight n to the negative the Euler characteristic, which will be n to the negative 2. So this explains how we compute the Wilson loop expectations of these complicated loops. And this kind of interpretation has immediate consequences. And we could prove many like existing results with very simple arguments. So by the way, this was the original calculation that you can do if you choose some representative theory path. For example, like you can use some iterated Ito formula and compute the same things using solving the ODEs consecutively. But okay, so So one implication of this interpretation is that, actually, I have different slides, so sorry for confusing you. But let's see. So we can immediately see that U of n and SU of n has almost the same Wilson loop excitation, but there is only different like exponential factor. The reason why this is true is because if you see the gluing rule that corresponds to U of n as U of n, then they are almost the same. So U of n basically glue your points in a naive way that like it is orientable gluing. But SU of n has another choice that you can just contract each other without gluing. So that factor, if you think of this Poisson sum, then that will contribute you to this sum, the total measure divided by n squared. And also you can easily see that the master field, so master field is where n goes to infinity. So basically in two-dimensional case, you can show that the Wilson observer without taking the expectation, the trace of holonomy will converge to some deterministic number. And we will call that as a master field. And we can show that master field for any Lie groups will be the same for the same loops. The reason is because if you take n goes to infinity, because we penalized the crossing or like higher genus surfaces by 1 over n squared, there will be no terms that produced by the surface with higher genus. So only genus 0 surface will contribute to this master field if you use our expansion. And that will be all the same for these classical Lie groups. So by classical compact Lie groups, I mean unitary groups, special orthogonal groups, and special unitary groups, and like yeah, something like this. So, and also you can show that the master field of multiple loops vectors through the products of master fields of each loop, and it comes from the same logic that you should have the minimal genus surface that produce these loops. So very recently, there is a proof of about this existence of master field on the higher genus cases, and there was a proof about the sphere cases too. So yeah, these are some correlates that you can immediately get from our interpretations. The next thing I want to talk about is the Gross-Taylor expansion. And as Scott already explained, so this is not the first attempt to try to explain the Wilson loop excitation as sum over some topological structures. And the most well-known in physical literature is the Gross-Taylor expansion. So the little history about this is that first Migdal and Witten formulated the Wilson loop excitation with reflection theory using lattice gauge idea and like using continuum limit to formulate this their formula. And if you see this Witten's paper, then you can see the formula for that in terms of reflection theory. And Gross and Taylor revisited this formula to give string theory interpretations. And it is very well-known result in physics literature. But the problem of this expansion is that there is some mysterious term, which they call like omega, which is like not fully geometrically interpreted. And they only show that by expanding this Witten's formula in terms of this sure biduality, and by making it in terms of the sum over some path in the symmetric group, they show that the like summation can be represented in terms of some sum over branched covers. And this branched cover also is not quite mathematically defined. So later Kors, Kors, Moore, and Rangulan, the same guys that Scott mentioned about the lecture notes, describe these weights as some Orphieford Euler characteristics. But this is also not satisfactory because this Orphieford Euler characteristics are in terms of like the space of surfaces rather than individual surface. And also they gave very heuristic and algorithmic way to describe this expansion. So for now, I want to describe in a very simple case where the group is U of n, and if your words doesn't have any inverses, then we can give some sort of Gross-Taylor expansion. And this is like the partial research is already done by Levy. And the way you use is using this ramification point of view. So suppose that you have some disk. So actually, I should explain another result first. Sorry. So when we showed, when I presented our result, there is actually some sort of correspondence between the transpositions or like some elements of a symmetric group and our gluing procedure. So that goes as follows. So suppose that you have some polygons that appeared in our result that in my description, and your original elements is just a symmetric group 1, 2, 3, 4 ... m, where there were like, let's say there were the length m words are given. And whenever you have some gluing, so here, this is for U of n case, you can think of this gluing splits your surfaces by 2. So if you record how this gluing changes your like outer boundaries, then first of all, if there were no gluing at all, then it will be just cyclic elements in the SM. But by making a gluing, you will separate this by 2 cycles. So it is basically corresponding to the product by transposition that corresponds to this gluing. So the resulting cycle will be just some transposition times the original group sigma. And you can keep going this. For example, if you have another gluing like this, then you will apply another transposition like here. And this will change your like boundaries like this. So basically, it will make your cycle as 1. So after multiplying these 2 elements, you will get just 1 cycle. If you think about this process in a calligraph of this symmetry group, where the calligraph is defined as you put an edge of the elements of that symmetry group if they are product by transposition. And whenever you go upward to the calligraph in terms of like the number of cycles decrease, you will get a extra genus, because multiplying by product transpositions will always increase your genus by 1 or decrease by 1. So if it decreases, then it will increase your genus of the resulting surface. So in this way, you can naturally make some correspondence between gluings of this gluings of edges and then the genus of the resulting surface. And you can also think of some path in the calligraph of the symmetry. And actually, there's a similar story in the ramifications. So suppose that you have some disk, and the origin, which is special point, is given by O. And suppose that you have some sheets, which is a covering space of this topologically. But suppose that you have some ramification point. So in a classical ramification theory, you can describe these ramifying coverings in terms of some braided diagram, and that will look like something like this. So suppose that we put a point O here, and suppose that you have some ramification. but we will restrict this ramification points so that its profile, so it only ramifies along the two sheets. So it will be unramified if you consider the inverse images of this ramified covering. And only like at one point, it will be ramified. And locally, this will look like z squared. And you keep put something like that ramified points here on the disk. And sometimes this might be ramified here, like this. And it also looks like z squared at these ramification points, but like in other sheets, they are not ramified. And in order to make, so in the original picture, you have some origin O, and there will be some points where this disk will be ramified over the ramification covering. And the way you can understand this as monodromy of this ramification. So you can pick some base point and you can think of some loops that around these points. And its monodromy will correspond to the transposition that will correspond to the like permuting these sheets on this braided diagram. And also another condition you have to impose is that once you follow this whole boundary, you should get the cyclic order, cyclic permutation again, that's like cyclically permutes these sheets. So if you multiply the total like transposition that corresponds to these things, and then if you multiply the monodromy corresponding to the origin, so this origin can be ramified arbitrarily, unlike the other points, which are simple ramification. So this should be the same as the cyclic elements. And this way, you can somehow make some bijection between the ramification coverings of the disk and the path that is defined from our like gluing process. And it turns out that these surfaces will like have the same, like gives the same quantity, although you weight by the n to the Euler characteristic of this one. So here, the Euler characteristic will be defined in terms of Harvey's-Riemann formula, and that will be exactly matches with that of here, the genus here. So in this way, we can prove somehow that our formula will give some interpretation of ramifying covering of the disk. And that is already done in the Lattice paper, but like we can also slightly generalize that formula because there he only considered where the loop is given by the winding of the same loops several times, where this, so basically this interpretation only works when you don't have the inverse, because if you have the inverse, suppose that you have like A and A inverse, then it will be not simply just like permuting your sheets. So it will affect other sheets too. So we can, in this diagram, there will be something like this. So if you glue two edges together, but in the UN case, and if they were the same, like let's say they were from the same alphabet A's, then they will be something like crossing each other. So it means if you multiply two transpositions, then it will give you the identity. But if the other one were A inverse, for example, then the first one gives you, it will be something like transposition, but the second one doesn't affect the final picture because they will just remain the same. And in this way, you can define some sort of semi-group action that acts on the symmetry group. So this is not just some like that of the calligraph of symmetry group, but it is a little bit more generalized version. And still we can write our summation as the sum over some paths on this pairing group action graph of the symmetry group. And in that way, you can somehow generalize this interpretation of ramified covering. But it is also not satisfactory because, for example, if you have some other relations, for example, if you think of G equals to SO of N, then some different types of gluing can happen. So in that case, you are not only just gluing this and this in an orientable way, but you somehow need to twist the other parts and glue to produce some sort of a Möbius strip. So in that case, you will get some non-orientable surface, and any ramified covering of orientable surface should be orientable. So this interpretation of ramified covering does not explain whole story if we consider other groups. So that kind of story is lacked in the original paper by this Langolam and Kors and Moore. So I think that is one interesting question you can ask. So what is the geometric viewpoint, or what is the corresponding picture when you glue that corresponds to our picture here? So we will give some like dynamics or combinatorics of these boundaries and how this genus evolves. And we don't have some geometric viewpoint how that corresponds to some geometric structure that we want, something like ramification points. So anyway, so that is the first part of the application. So I think I will show you the more formal writing later. And the next applications is the Markin-Miglal equation that Scott mentioned. So let's go to the slides. So the Markin-Miglal equation is some sort of variational formula that is very useful to compute the Wilson loop excitation for complicated loops like this. So the idea is that whenever you have some simple intersection like this, where your original loops were, so your original loops were going like this, and you somehow want to take the variations near this point. So the way you variate this is that you decrease the areas of these two faces slightly by like epsilon for h, and you increase the F1 and F3 by epsilon by doing this. And if you take these variations, then what you get is actually the product, or like, or the Wilson loop excitation of two separate loops. So effectively, this formula will decrease the number of intersections, because originally you had the intersection here, but after applying this variation, what you get is this red loop and the blue loop. So by separating these two loops, you can reduce the number of points, and using this algorithm, you can theoretically compute any Wilson loop excitations. And for I will explain why our formula gives a very simple proof for this variational Markin-Miglal equation. And to illustrate how it works, I will just focus on the U of n case, where everything is very simple and there's no extra term. But the idea is basically the same. So in order to explain how this works, I probably have to explain a little bit more about how we chose this basis of the graphs. So as I said, we want to somehow decompose our original complicated loops in terms of some disjoint loops. And here, so there should be some canonical way to decide such a decomposition, but it is not unique, and it depends on the choice of spanning tree. So the reason why it can be determined by spanning tree is, for example, suppose that you have some spanning trees like this on your complicated loops, and you can think of some Dürer spanning tree of this graph. And then suppose that you want to express your edge here in terms of the products of the lasso bases or like the faces inside, then one obvious thing you can do is just do the loop here and then go backtrack like this. So here the bold black lines are in the spanning tree side, so we will ignore those parts. And by multiplying these two loops, you will get this blue edge as the product of two loops. So basically, if you have some sort of like wedge type of things in this your spanning tree, you can just product everything following the order of this your spanning tree to obtain the face product of this representation for each edge. And basically, if you do that for every edge, which is not in your choice of spanning tree, then you will get the lasso basis or like lasso representation of your original loop. And so this is the two different picture where I draw a very small circle around the intersection. So the original loops were written here, drawn as the blue lines. And the variational curve is drawn as the red one, so that you decrease the area by epsilon here, and then of these two areas, and then you increase the areas on the other side. So for other parts, it is the same. So actually it should be, yeah, go like this. Yeah. So is this picture clear? And what we are trying to do is write this in terms of lasso basis using some additional epsilon area faces. So in this case, so the only different parts is around this intersection. And let's say we label these faces lambda 1, lambda 2, lambda 3, lambda 4. And instead of choosing this path, we chose the other one. But because we can make our choice arbitrary to choose the spanning tree to make the complete computation simple, we will choose tree like this. Then the original surface or original curve will correspond to this type of lasso representation. So this is the reason is because we have to add this edge, this blue edge. And this blue edge, as I said, should be represented by a product of these two faces, which corresponds to this part. And this also has this loop, which is also the which can be represented as a product of this one. And yeah, so basically, if you compare this this variation, like this red curves and the blue curves, the only different parts will be represented like differently in terms of lambda i's, which has infinitesimally small areas. And we want to compute the Wilson loop coefficients of each ones. And there are three possibilities. So the first possibility is that if you choose the Poisson point process and the gluing happens among these lambda i's. So if there is no such gluing among these lambda i's, then everything will be the same condition of this event. So we can ignore this event. And if there is more than two gluings among these lambda i's, then they will contribute to like epsilon squared. So in this case, for example, lambda ones, and if there are two gluings like this, then they will contribute to epsilon squared because their areas were epsilon. So we can also ignore that part. And conditions on there are only one pairing, like here, there is a lambda 1 here. So the different parts here is that there's no lambda 4 pairings on the left-hand side, so in the original curve. So the existence of this new pairing of lambda force will be only difference between when you compute the Wilson loop expectations of both curves. And basically, if you consider the condition that there is a gluing between lambda 4 and lambda 4 inverse, then it will effectively divide your curve by 2 parts, because whatever you have among these 2 parts, they will make some genus, they will increase your genus by crossing this line. So the surface that is made from gluing from other parts will be penalized by 1/n² factor, as I explained. So if you, for example, consider the master field equation, then that part will be 0 exactly. So that will give you the Markov-Migdal equation that the variational form is equal to the product of two different the Wilson loop expectations. And if you consider the finite n case, then you will still have the interpretation of the expectation of trace of 2 different loops. So product of trace of issued loops. So this will simply prove the Markov-Migdal equations. And the previous proofs all relies on, as Scott said, representation theory, and they use this driver sancta formula, and they use some sort of variations on using that formula. So I think our proof is more probabilistic, and it's quite easier to extend to other parts, because basically this gluing procedure is almost the same for other groups. And this part is something that I mentioned before. So using Schur-Weil duality, you can determine some correspondence between the conjugate invariant objects in the unitary group and some simple walk on the symmetric group. So yeah, I think yeah, we could define some. So this was our main result, that the Wilson loop expectation can be represented as sum over some path on the action graph, where this semi-group action that as I described, acting on the symmetry group. So if you can convert your Wilson loop expectation sum as the sum over this random walk on the action graph. So as an application, you can actually compute any Wilson loop expectation by first figuring out what is the action graph corresponding to that. So this is one non-trivial example that couldn't be done in the Levis formula, for example, because he never considered this inverse type of relation. So this is the action graph corresponding to this loop. So as you can see, if we, for example, if this gluing was orientable, or if it were the same A's, then applying two A's will give you the identity. So that will effectively decrease. So if it were not A inverse and A, then your next A will send you again to the above, and that will increase your genus. But it has different type of action, and it will actually make you stay in this forever if you apply A more times. So in this way, you can somehow construct some action graph corresponding to your given Wilson loop. And if you have this kind of graph, then the weighted sum can be easily computed in terms of this adjacence matrix. So for example, for this graph, the previous graph, whenever you have the edge, you can weight that by the corresponding area, and that will form you some adjacent matrix given by this. And you can easily compute the Wilson loop expectation using the exponential of this adjacent matrix. So this will give you actually the same form that I have presented. Okay, and also, yeah, I forgot to mention that if you're interested in, so when I describe these ramification points, point of view, it is actually quite similar to the usual setting of Hurwitz problems. So Hurwitz problem generally asks you how many ramifications over some surface given some ramification profiles. So in our case, there like we impose that the origin can have arbitrary ramification profile while the others are simple. And this is almost the same as the classical Hurwitz problem, except that we like in that problem, we want to make the ramification covering is connected. So they should act transversely. So like, I think if you're interested in that kind of relation, you can read this paper by Nathanjon. He explains how this integral over Gaussian matrix is related with these Hurwitz numbers and how Yang-Mills probably related with that problems. Also, yeah, Okunkov also explained this kind of Hurwitz systems and Gromov-Witten theory. This might be related with this. Okay. So how many minutes do I have? Like 5 minutes?
Exactly.
Yeah. So I think I can try to explain how to prove this main theorem, which is basically just some simple random approximations. But I think that will then I should spend more time. So I will just try to finish my talk by questioning some open questions. So we basically, our result only applies to the plane case. The reason is because we rely on the fact that the simple loop on the plane has the holonomy of this simple loop is the same as Brownian motion on the Lie group G we choose. But actually, for example, if you think of sphere, then there the loop might have two sides, so it does not have the infinite area of phase. So here, this holonomy of the loop will have some law of Brownian breeze instead of Brownian motion on the Lie group. So, like you can try to do similar things, like by taking a puncture or something like that to reduce this problem to the plane case. But as far as it is not that simple to reduce the same framework. But it would be really nice if we can generalize this result to sphere or higher genus surfaces. And also, as I already asked, it would be nice if there is some interpretation geometrically how the Gross-Taylor expansion is explained more mathematically and in terms of geometric point of view that matches with our combinatorics. And also the only reason why we take care of this kind of 2D-dimensional case is try to understand higher dimensional cases like 4D, which is the most important. And we hope this kind of research can give some hints how this continuum limit of some of our string trajectories is related with our this continuum limits. And and we also, because these results are basically in a realm of these matrix models, so-called, so basically the Yang-Mills function can be represented in terms of integration of random matrices or something. And there are so many models that have the similar structure and have the similar techniques to compute this kind of expectations or traces. So we hope there might be some bridge between the other models, and we can just extend our techniques to there to see if anything is related. Something. Yeah, so I think that's all of my talk. And are there any questions?
Thank you very much, Minjae. As he asked, are there any questions of the audience before I start? Maybe I can start with a simple question. So I don't understand exactly what you get. I mean, what do you mean by Brownian bridges, in the sense that you are usually, for the Brownian motion, you are looking at a given time, no?
Right.
But for a Brownian bridge, are you looking for you cannot look for the end time. It would be 0.
Yeah.
in a
So
certain way,
basically, what you have is, if you have
Identity.
area A and B on the two sides,
Yes.
then your Brownian motion should go back to the identity at time A plus B. So this is also quite obvious from this driver-Sengupta formula. So the driver-Sengupta formula works for any manifold with any dimension, or any, like, not dimension, any genus. So for example, sorry. Yeah, if you see this formula, then this part is like, you should product these heat corners, evaluate holonomies for every bounded phases. So in the case of plane, you have infinite phase, so you don't need to take care of that. But because of in a sphere, you have two bounded phases that shares this loop. This law should be the same of that of the Brownian bridge in the Lie group.
In a way, it is the time is given by probably the time A, no, or somehow related to this.
Yes.
So the length is A plus B, and the time is somehow A.
Yeah.
Or
Right.
not? Okay.
Right. That's correct.
I see.
I
And
think there's some question in the
Yep, sure.
audience.
Thanks. Yes, I have a question.
Yeah.
It was a great presentation. Thank you. The question is there any difference here between lattices in real and complex space? Is it possible to extend this to complex spaces?
You mean like for the Lie group, you will change the...
In any case, at the end, you naturally discussed extensions to higher dimensions, but is it possible, does it make any sense to extend this also to complex lattices, in this case?
Yeah, I think like basically Levy's research is dealt with any like fields. So if you want to change the basis of these Lie groups, then I think almost the same research will be obtained.
Okay.
But I'm not sure if like basically we have, if you change the bit like the real parts of the space, then we will change the dimension, and I don't think there will be nice results.
Thanks.
Yeah.
Okay, I have sort of a very naive question. So, so Scott mentioned at the beginning that kind of big question in the area is imagine a continuum version of this Yang-Mills theory. And so with this representation as a sum over the random surfaces, does it help answering this question?
Oh, so you're asking how this can answer Scott's question?
Yeah, well, I mean, does it help? Is it easy to imagine sort of a continuum version for this representation?
Yeah, so like basically one thing that is not clear even in 2D case. So if you think of this Cherge story where you consider the lattice gauge theory, then basically there will be a lot of like a lot of surfaces that will be not counted in the Wilson fixation in the end. So for example, suppose that you have two independent like plaquettes like this. In terms of our like in the continuum setting, they will have like independent Brownian motions as a holonomy. So you will have independent like laws, but like so basically to compute the Wilson loop prediction of these loops, then you will just multiply these two things. But for the Cherge story, there might be some like crazy strings that connects these two things. So it's not clear why these are independent. If you just naively take the continuum limit their side, and like how this like crazy surface will be canceled, and you can only consider the minimal surfaces that matters, is one of the like important problem to answer.
Mhm.
So I think in that sense, it might help something, but like basically for higher dimension case, I think we need totally different techniques or something.
Sure.
Yeah.
See. Thank you very much.
So are there any other questions from the audience? So I don't know if Andre is he
Yeah,
has
I
his
think
hand
that's-
eye, but I don't know if
Then-
it stayed.
That's an old one,
Yes.
yeah.
Yes, thanks.
So if there are no other questions, I propose that we thank Minjae Park for his really good talk. Bye.
Thanks.
I would invite all of you for a coffee here, but you are a little bit far away.
Yeah.
So thank you very much, both of you, for your talks on. We learned a lot about two-dimensional Yang-Mills theory. Thank you.
Right. Before you go, can I ask, are you
Yes.
happy with your slides being uploaded to the website?
Yeah, it's okay. But let me
Yeah.
see.
Okay.
Yeah, there are some. I mean, it's a little bit messy because we didn't manage to make it one. But
Wait, I mean, if you want to make changes, that's fine. Just send me an updated one.
yeah,
once
but
you're done.
I think you can just upload that one if Scott agrees.
Yeah, that's fine. That's fine.
Okay.
Okay. Thank you very much.
Thank you very much. So see you soon.
Yeah.
I hope in person next time. I'd like
Yeah,
to
thanks
see
for organizing. It was fun to see people.
Should we stop the